Hello, everyone. I want to talk a little bit today about science. Kind of introduce you to some of the terminology that we use in the sciences. These are useful, I think, for everybody to know. A couple things really quickly. I just want to kind of plug some of my other classes for those of you who might be still juniors. We do have a creative writing minor starting up here at UB. I've been developing that and teaching classes in it. So if you want to learn how to write poetry and fiction, you can always take a creative writing class with me. Also, I'd like to plug one of my colleagues' classes. If you're interested in film or gender studies, I do recommend taking classes with Dr. Saskia First. She's a good colleague of mine and a good friend. So anyway, plugging aside, I want to kind of just say that even though I teach in the humanities and teach creative writing, I have a lifelong love of science since I was a kid. Um, Even memorizing the Latin names of dinosaurs, studying astronomy, spending just countless hours outside, um, learning and watching the heavens and all that. My first PhD was actually in philosophy of science, which is a little bit different from science, which we'll talk about here in a bit. My second PhD was in English literature, and I actually almost did a third PhD in evolutionary biology, but it was a 4-year lab class, or would have had a lab degree. So I kind of passed on that. But so I have a lot of ground in all of these disciplines, and I find all of them really fascinating. So to go through this, since many of you in the class are in the sciences or social sciences, I think that this actually could be pretty useful. Just learning how to understand science. What is its point? What when we talk about science, what are we actually talking about? How does science know what it's talking about? So these are all kind of based in the philosophy of science, and this will hopefully help kind of outline some of the debates that we see going on in people who challenge the sciences and say, oh, that's just a theory. And how does science respond to that? So, well, let's ask the question. What is science? It's actually a harder question to answer than it might seem at first, because the practices of science that we more or less take for granted today took centuries, if not millennia, to develop. We talk about the scientific revolution. We talk about how the Renaissance allowed that. And this was, where science has really, in its current form, only been around for maybe 150 years. It starts about 400 years ago, which I'll discuss. It has some of its roots, though, even up to about 2,000 years ago. Years ago. So, for example, it's popularly, assumed that up till more recent times, everyone thought that the Earth was flat. You'll kind of hear this. Even for some reason, there are still people today that think the Earth is flat. I have no idea why. That this is not true. The Greeks, going back to somebody like Eratosthenes, the Greeks knew that the Earth was round. That's pretty clear. I mean, if you think about the Greeks, they were a naval culture, right? And you guys can see this even, for example, on a cruise ship. When a cruise ship is sailing across to the horizon, right, you'll notice this, that you'll be able to see all of the cruise ship, right? And then as it goes over the horizon, you're only going to see parts of it, right? And then by the time it gets farther and farther away, you're only going to see maybe the stacks of that cruise ship as it goes over the horizon. Why is this? Because the Earth is curved and you have only about a 12-mile visual reference out to the edge of the horizon. Okay, so the Greeks knew this, and not everybody thought the Earth was flat. That was the Europeans. Um, Now, the idea of scientific inquiry, okay, actually has some of its roots, as I said, in this fellow named Eratosthenes. He actually figured out to an incredible degree the circumference of the Earth. What he did was he took 2 points, I believe it was Alexandria and Syene in Egypt, and he very carefully figured out through other mathematicians what the distance was between these 2 points. Then, at a very specific time, on both in both places, he put a gnomon, which is a kind of pole, into the ground, and then measured the angle. So here's the sun. He measured the angle of the shadow at noon on each, which allowed him to figure out. So if that's like 7%, right, and this is 7%, that allowed him to figure out, okay, if I know the height of this, I know the angle, right? I know the percentage of the angle here, and I know the distance. I should then be able to calculate the rest of the circumference around the remainder of the Earth. There's another kind of variation on this. I believe it was in Alexandria, where they figured it out by a well. And there was, the sun is going over the sky like this. At a certain point in the sky, the sun is going to be directly above. So if you know that when that sun is going to be directly above, and then you can determine these shadows, right, where they're falling versus where it's going to be at noon, that allows you to approximate, right, the percentage of curvature, right? If you have 2 different wells, and you say, oh, okay, at noon it's above here, but at noon over here, right, it's casting this shadow, right? That allows you to, once again, kind of approximate part of the circumference. The Earth here and sun are not to scale, probably. Ha ha ha. Okay. So anyway, Eratosthenes runs this, and actually he calculates that the Earth's circumference was 39,375 kilometers. This is amazingly close to the actual circumference of the Earth, which is 40,000, and that's 4. My handwriting is terrible. 40,076 kilometers. So I believe he's 1.4% off. And this is 2,000 years ago. This is somebody using literally poles in the ground, right? That's pretty incredible. Okay. So what happens when you know the circumference of the Earth? Well, it's a piece of knowledge. It's a piece of data. It's something that we can't necessarily refute. Okay. And that's not bad for somebody who lived 2,200 years ago. Sorry, it's not 2,000, it's 2,200 years ago. No GPS, no telescopes, no knowledge of the rest of the world. I mean, all of this was unknown to him, right? So he's basically assuming something. He's assuming qualities of nature that he has to then assume are consistent. If there was a giant chunk missing out of the Earth over here, right, the circumference would be different. So he's assuming a kind of consistency in nature. And this is something that all scientists, right, have to assume when they present hypotheses. There's a continuity and a consistency about the Earth, about nature, about the universe. Now, it's an interesting premise upon which science balances its forms of knowledge, right? If we determine that something's true of the world here at this time, we assume that it must have been true elsewhere on the planet, or even in the past or the future, right? For example, it's a kind of interesting idea, but the Earth, right, is spinning, right, and our day is 24 hours long, right, approximately. It's a couple seconds off, which is why we have leap year every 4 years. So the Earth actually has been slowing down. So maybe 200-300 million years ago, the days would be a little bit shorter, right? And in a couple 100 million years, the days will be a little bit longer, okay? So this is just things that we have figured out, okay? But in general, science has to assume this kind of continuity this kind of consistency in nature. Um, but yet, don't we assume that science speaks in truth and fact? I mean, this is what we hear, that, oh, it's a scientific fact that, blah, 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 blah. It's true. Science says so. Well, the world as we know is constantly in flux, right? Things are constantly changing. I mean, if the length of the day is changing, how can we be sure of anything? What was true even 100 years ago, according to science, may not be true now or in another 100 years. What we observe and experience requires an explanation, and our explanations can always be wrong. A scientific explanation can always be wrong. So why do we give so much deference to science for its facts while the rest of us wander around in constant uncertainty? Part of this has to do, okay, with the scientific method. Now, I'm not going to go into, not methods, the scientific method. Let's make it a capital M so it looks more important. This is a general movement in history that I will try to kind of sketch in a bit. Now, as an introduction, it's important that we begin with what's called an epistemological question. How do we know what we know, and how certain are we that we know it? Okay. This is something that I'll just use this example from Isaac Newton. You can see here, not all that easy to draw. I'm usually a little better on these digital whiteboards. So Isaac Newton, one of the smartest people to have ever lived, wrote this book called the Mathematica Principia. Now, he actually wrote this in order to explain celestial motion. And in doing so, he came up with gravity as this kind of unifying force. Okay, Newton saw the moon one day, right, passing overhead, and it's true that this little apple, right, fell near him. It didn't. I mean, it's usually represented that it bounces off of his head. It fell near him, and it got him thinking about the relationship between how the moon moves in the sky, what's holding that, what's moving that, and how things fall on the planet. Okay, how does gravity work? How can he use that to explain all this celestial motion? Fun fact: Newton actually, when this happened to him, he was, I believe, around 24, and he was staying in a farmhouse, right, kind of outside of the cities, because at that time there was a really bad outbreak or plague going around. So he went out there to kind of take a break, get away from everybody, and not get sick, much like we're all doing right now. So plagues and viruses, these are nothing new to the world. Okay. So anyway, there's Newton. He writes the Mathematica Principia. If you took physics in high school or college, you've studied Newton, you've studied some of his formulae. These actually are still pretty accurate. You can use them to make very accurate predictions about certain types of motion. We even talked about Newton's laws, right? This is back when people thought that science could write or figure out the laws of nature. We don't speak in terms of law anymore, and I'll tell you about why we don't do this here in a moment. Well, here's why. Well, if you speak about laws, right, here comes Einstein, right? And he says, oh, well, Newton's all good and all that, but what about space-time? And he comes up with this notion, to put it very briefly, that time and space are actually interwoven, right? And that they interact with gravity. So the more mass something has, okay, the more specific gravity it has, and therefore the more it is warping space-time, okay? So, and this has to do, it's actually really, really complex. It also has to do with the speed at which something is traveling. So if you are traveling faster and faster and faster, right, approaching the speed of light, c, then time will slow down. but the energy required, if you have any mass, right? The energy required to get you up to the speed of light becomes exponentially, because here it's squared, becomes exponentially high. This is why, for example, photons move at the speed of light, because they have no mass. Okay. So we can get going very, 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 very fast. Okay. But as we do so, time slows down. It's a very weird concept. Okay. So here the apple, right, is interacting with this kind of fabric of space-time because it has mass and therefore weight, so therefore it affects space-time. Planets, okay, being much larger things, do affect space-time. You can run this experiment as they have, right? You can take a cesium clock, super accurate. It's basically an atomic clock. And you calibrate it down here. You send it up in a space shuttle, and you let it run around because it's moving fast up here, and it's not as close to the Earth's gravity. The clock, when it comes back down, will be a little bit slower, okay, because it's not being acted upon by gravity. It's moving quite fast up here. So, I mean, they've done all kinds of experiments to prove that this whole relativity thing and Einstein's idea were correct. So, but Einstein's model of relativity completely broke Newton's laws. It rewrote our understanding of time and space. Now think about it this way. If Newton was right for centuries, right? We have called all the things he did laws. And Einstein comes in and he says, nope, Newton wasn't right, I'm right. How can we ever determine whether something's actually right or just provisionally right? Will Einstein be wrong next century? Is somebody going to come along and find a better explanation for the universe? Okay, this is what things like string theory are seeking to do. String theory it's actually a mathematical principle more than it is science, but I won't get into that. I don't like string theory. Anyway, but this is particular to how science works. Like I said, we used to speak of laws. The law of nature, Newton's laws, etc. Today, we speak of theories, okay? Because in science, we don't like to speak of a law because we have to be a little bit humble and realize that, yeah, we could be wrong. We've been wrong before, okay? That means that science, okay, has to be, to give you a $4 word, corrigible, revisable, okay? We put out hypothesis X, okay? And then we learn over the course of years and study and facts and gathering facts that, well, we were a little bit wrong, so we have to modify it, right? Now, the core principle might remain correct, but it becomes modified. It gets new iterations as it goes forward, right? In science, we're constantly testing our hypotheses. And this is just how science works, okay? Now, it doesn't mean that it's incorrect. It means that scientific hypotheses have to remain open to revision and correction. That's what the corrigible idea means. Now, I'll talk more about this later, but science has to be, like I said, falsifiable and fallible. Fallible means correctable. Falsifiable here means it has to put forth, right, an idea. X is this way that we can test, okay? Because if I can't test a scientific hypothesis, it has no validity as a scientific hypothesis, right? Other people have to be able to come in and test what I'm saying and therefore try to prove it incorrect. Okay, they're not trying to verify it, they're actually trying to prove it incorrect. And the more that a scientific hypothesis withstands falsification, the more, the better, how to put it, the stronger our claim becomes, okay? So I'll talk a little bit more about that and the relationship to Karl Popper as we go on. So, like I said, science has to be fallible, has to be falsifiable. Now, here's the problem. If everything is potentially revisable, if science is potentially revisable or corrigible, how can we ever actually say that we know something to be true? Well, this is welcome to the philosophy of science. Okay? Scientists don't actually, any of the scientists I know, they don't worry too much about these things when they're conducting their astronomy or genetics projects. But in philosophy of science, we worry about these things quite a bit. And actually, I think is a pretty fascinating subject. So I'm going to pause this here and I'm going to do a part 2 here. So I'm going to break this into 2 smaller lectures to kind of get us going as far as how to understand the aims of science and how it works.